So good morning all, this is Shreyas and I'm back. Today we're going to understand mathematics, its branches and its real world application. So this is another standard 10th project. You guys can copy or refer to it. Let's get started. So first of all, I bet most of you guys hate math. Maybe because you guys score less. So do I. But the point I'm making is that this subject is one of the most applied subjects in our life. From buying groceries to sending rockets up to space like Chandrayaan 3. It all has math in it. And that's one of the few reasons I love maths, because that's one of the few subjects that actually have a real world application that we learn in school apart from science. Even physics in science, it also contains math. So that shows how important math is in our day-to-day life. So in this project, in this presentation, I'll try to make you guys fall in love with math too. I know that's a bold statement, but let's get started. So first of all, the introduction or topics for this presentation. So first of all, I'll talk about cryptocurrency and maths, which is making millions or losing everything. Then we'll move on to topology and shapes. And topology is kind of a weird subject, but I'll try my level best to explain it to you guys. Then we'll move on to quantum computing and understand some principles of quantum physics, which I personally find most fascinating. And yeah, it's just amazing. So let's get started. So first of all, cryptocurrency and math, making money or losing it all. So before moving on to what is cryptocurrency, first let's understand that what is cryptography. Cryptography is the science of using mathematics to encrypt and decrypt data. So what do I mean by that is, cryptography heavily depends on the number theory, and well, we'll go on to this later. First let's understand what does encryption and decryption means. So this is a decrypted plain text. It could have some message like ABC, hello, and then it gets encrypted, which is it gets turned into a code, which is 00011. I hope you guys get it. So via this public key, it gets turned into a code, and the code, well, we cannot write it as code, right? Because it is plain text. So instead of writing it as code, we write it as ciphertext, and ciphertext is nothing but the coded or encrypted form of plain text. So now the ciphertext is made, no one can actually read this message. So if the plain text said that I love you or ABC or hello or how are you, then no one could actually read the ciphertext now, because it's encrypted. It is in the form of numbers and alphabets and maybe some signs, so no one can actually read it. So that's like a secret message. Now only the person that is intended to read the message or to understand the message can read it. And in order for the person to decrypt this message from a ciphertext to a normal plain text so that he can read, they would use a private key or the solution of this encrypted message, and by using this solution they would get the plain text back, which could be any message. So here's an example. Let's say I want to send someone this message called ABC, and what's the place value of A? It is 1. Place value of B is 2. Place value of C is 3. Let's say that I may make a code which adds 1 to the place value of these digits. So place value of 1 is A is 1, so 1 plus 1 2. So the code for A is 2. Simultaneously, code of B is 3, code of C is 4. This is the code for the following message, or this is the encrypted form of the following message. Now we decrypt it, and in order to decrypt this, we need the solution, which is the private key. As we cannot call it solution, it would not sound cool, right? So that's why we call it the private key. And when we implement the private key here, we get A, B, C. Now the formula was really simple. Get the place value, add 1 to it, and yeah, here you go. This is your encryption. Now, even though this sounds easy, that's not actual cryptography. This is just an example to make you guys understand. Now, as I told you, cryptography heavily depends on number theory. So what is number theory? So number theory is about numbers. It's about prime numbers, composite numbers, square numbers, triangular numbers, whole numbers, natural numbers. It's all about numbers. And that's why it's called number theory, and it's a whole big topic in itself, so I cannot teach you guys that. So if you guys are actually interested in cryptography, you might need to search or research on number theory on your own. So this was all, and then there are some encryption methods which are SHA-1, SHA-226, SHA-256, SHA-384 and 512. So these are a few encryption methods. The most commonly used is SHA-256. You guys can it's also called as secure hash algorithm 256. And yeah, this was all for cryptography. Now moving on to cryptocurrency. So the best example of cryptography could be nothing less than cryptocurrency itself. And I know it's like quite a heated topic, and I don't promote anything about cryptocurrencies, so keep that in mind. And so cryptocurrencies is nothing but cryptography plus currency. So it's a currency which revolves around cryptographic functions. And even though it's a lot complex, I'll make it simple for you. It uses something called as a blockchain, where you have these blocks, and these blocks are in a chain. That's quite self-explanatory, but still, they're in a chain. And if anything goes wrong here, the whole blockchain collapses. This is why it's the most secure way of transaction, even though I do not promote this. And it is decentralized, so no particular agency owns it, and that's why it is really volatile. That was all. Don't trade in cryptocurrency. That's all. Yeah, and we move on. So now topology and shapes, and it's geometry, right? Because look, topology is also a study of shapes, but it's not the way you think it is. So to a topologist, a donut and a cup is the same. And now this might sound absolutely weird, because a donut and a cup, they're like so different. But a topologist considers that anything that they examine is made of clay, but the clay cannot be cut, cannot get poke, you cannot poke holes in the clay. All you can do is move the clay. You can just mush it around, but you can never poke holes in it. You cannot cut it, you cannot join it. So these are some rules before we start learning topology. So this hole in the donut represents the handle. So if we were to take all the matter from one side and then make a cup-like structure on one side and then keep the handle as it is, then it could become a cup. So that's how topologists look at the world. But I mean that's why I call it weird, right? Because a cup and a donut is the same. Yeah, that's kind of weird. And then what are the applications of this particular subject, because it's so weird, right? So yeah, there are a few applications. One of them is in biology, where you study the splitting of DNA and maybe nuclei and genetic structure. So it's about splitting of cells. That's what you study in topology in biology. That's the application of topology in biology. Then moving on, you also have some applications in physics, because when you study materials or matter at a really high temperature or really low temperature, they start to act volatile like squishy clay, and that's all topology is. So this was all. And now, as I told you, topology is a study of shapes, but it is not geometry, because as I told you previously that a topologist considers anything that they see is made of clay. So for them, a square and a circle are the same, because they can mold the circle into a square and it would become a square. The area will not change because they cannot cut away pieces. Remember? That's why a topologist considers a clay and a square, a square and a circle equal. My bad, I'm sorry. And in case of geometry is more concentrated at accuracies. So you might also get asked questions that to find the area of this or surface area of a particular solid to the nearest decimal. That's because we are concerned about accuracy, the accurate measurements. But in topology, it's not like that. It's a relatively young subject, and that's the reason why it does not have much applications. And you guys might go that I'm not telling you guys the formulas, and that's because if I told you guys the formulas, then this presentation would get utterly and absolutely boring, which I don't want. So that's why I will not tell the formulas. If you guys are actually interested, you guys can actually deep dive into what topology is and understand how a square and circle is equal in topology. Moving on, quantum computing. So first let me tell you guys what does quantum means, because that's like even though it might sound like a buzzword, quantum computing, quantum physics, quantum this, quantum that, but what does quantum means? Well, let me give you an example. What is a quantum of light? That is a photon. What is a quantum of matter? That is an electron. Maybe it's a quark, but let's just say it's an electron. So quantum is the smallest particle of anything. What is the quantum of water? Well, that's also electron, because again it's H2O. And then if we grab electron from any of those uh, revolving revolving planets, then yeah, that's an electron. That's the smallest possible unit of a particular state of matter. That's why it's, for light it's photon, for matter it's electron or quark, and so on. That's quantum. What does quantum computing does? What quantum computing does in a nutshell is it exploits a few quantum principles like superposition and quantum entanglement, and uses it to do calculations. So this is Sycamore, which is Google's quantum computer. I know, like, that's like a really cool name, Sycamore. And this particular computer did a calculation which was supposed to take 47 years in 47 seconds, and that's exponentially fast. That's because this computer does not uses classical bits like 0 and 1. These are like obsolete for these cool computers. They do not use this. They use qubits, which you can call the elder brother of classical bits, because for classical bits you have two possible outcomes: binary, 0 and 1. But for a qubit, you can actually have four possible outcomes, which is first of all 0 and 1, and then 0 1 and 1 0. This is the fascinating thing about qubits, because they can actually use superposition and can exist at two states at once. And this is why this quantum computer can do calculations exponentially faster. So moving on, let me just tell you guys what is superposition, so you guys might not stay confused for a long period of time. What is superposition? Let's say I have a coin, I flip it, and we know that coin lands heads or tails. But in a superposition case, the coin would land both heads and tails. I know this sounds weird. So let's look at it this way. I flip a coin, I clamp it between my hands. It's between my hands, right? I open my hands and it's tails, or maybe it's heads. But as long as that coin was clamped between my hands, it was either heads or tails. So between my hands, the coin is either heads or tails. It is not defined as long as I open it as heads or tails. This is superposition. The coin is existing as both heads and tails until I open my hand. And well, that's heads. This is superposition. Now there is this experiment called Schrödinger's cat experiment. You guys can understand this yourself. It's the same experiment as a coin, just it's a bit more complex and techy. Moving on, as I told you about quantum entanglement, let me just tell you guys or make you guys understand what is quantum entanglement. So two coins, again we are using coins because they're the most simplest way of explaining. Two coins, heads tails, flip, and somehow both coins always land heads or tails. They are never different. They never land opposite. They never land tails heads or heads tails. They're always heads or heads tails. And this is quite strange and spooky, because that's a coin. It cannot. Those coins at least should once at least land opposite, but they never land. That's because they're in a quantum entanglement. Their fates are entangled they can communicate with each other. So if I were to take a coin on the North Pole and one coin at the South Pole, and I flip both of them, somehow they will communicate to each other, telling that, bro, I'm heads, so you have to land heads too, and the second coin will also land heads. This is quantum entanglement. Their fates are entangled, and this is just amazing. So even though you take it anywhere in the universe, one could be in the Andromeda galaxy and one could be in the Milky Way. Flip both of them, they will always land heads or tails. That's quantum entanglement. So this was all for this presentation. I hope you guys liked it. Thank you. Bye bye.